Here we are. We have arrived at the last chapter in the book. You've had almost a full year of studying chemistry now, and we are now down to the topic of chemical equilibrium. We just finished talking about reaction rate in the last chapter, and chemical equilibrium is very much along the same lines. The difference here is that we've been kind of telling you all along, and the assumption that we've been making is that a reaction goes to completion and gets finished, but in reality, that's really not true. What happens is that we talked about the collision theory in the last chapter, and we talked about how molecules have to collide. They have to collide often enough, they have to collide hard enough, they have to collide in the correct orientation in order for products to be made. Well, if you can picture this in your imagination, what happens is that eventually you have enough products that are there, and they're moving around and they start colliding as well. And so it is very possible that some of those products will then collide in certain ways and turn back into reactants. Now that may seem a little strange, but that in reality is what happens. And so what happens is that you've got your reactants turning into products at the same time that you have your products turning back into reactants. And so you're probably sitting there going, well, Mrs. Thompson, everything that we learned about all that stoichiometry then doesn't even do us any good, because if things don't go to completion and the products start turning back into reactants, how do we know how much we end up with? Well, we will actually address that a little bit later on in the chapter. But for today, what I want to discuss is what equilibrium actually means and how we can display that in a mathematical formula. So at equilibrium, when you start the reaction, your forward reaction goes at a quicker rate and the reverse reaction is not happening at all. Eventually you have enough products that the reverse reaction will start to occur. So at the beginning, the forward reaction is faster than the reverse reaction, and eventually you will get to a point where the forward reaction and the reverse reaction are happening at exactly the same rate, and that is called equilibrium. So your forward and reverse reactions are equal, and what that means is that the amounts of each substance, product and reactant, no longer change. So when you normally think of a reaction, your products are the ones that are being formed and reactants are getting used up. But when you have an equilibrium situation, you have some of each present and the amount doesn't change. Now that doesn't mean that there's nothing happening in the container anymore. It's just that as fast as you're making product, you're also turning around and making reactant. So the total amount doesn't change, even though the individual molecules may still be flipping back and forth. Okay, so these two things are true at equilibrium. The rates of the forward and reverse reactions are equal, and the amounts of each substance are not changing. Now, just like we had a rate constant to talk about the rate of a reaction, we can have an equilibrium constant, and you'll find a lot of similarities between the two of them. First of all, both equilibrium constants and rate constants are dependent on temperature. And since an equilibrium constant takes place at a time when the rates of the forward and reverse reactions are equal, hopefully that should make sense to you because we're still talking about the rates of reactions. And so if I change the temperature, the equilibrium constant is not going to have the same value. Both equilibrium constants and rate constants involve concentrations of reactants and products at a particular point in time, but there is a key difference between the two of them. We did a lot of problems in chapter 15 where we were calculating rate constants, but I told you that you had to have data in order to calculate what the exponents were in that rate constant to figure out what the order of those reactions were. If you recall that, we had to use experimental data in order to calculate that. With equilibrium constants, we are now able to utilize the stoichiometric coefficients that are present in the reaction. So it's actually a little bit easier to figure out what the equilibrium constant looks like than it is for a rate constant because we don't have to have experimental data in order to do that. So another thing to keep in mind is that all reactions are going to be equilibrium reactions, And a lot of them are going to go a lot more to completion than others. And like I said, we'll address that a little bit more a little bit later in the chapter. So for right now, what I want to do is go through a couple of problems where I show you how to calculate an equilibrium constant. And if you pull out the sheet that I sent you that has the sample problems on it, you will find these printed there. So the first problem says the following reaction, which is nitrogen gas reacting with oxygen gas, which yields nitrogen monoxide, reaches equilibrium when the concentration of nitrogen is 0.354 molar, the concentration of oxygen is 0.124 molar, and the concentration of NO is 4.51 molar. What is the equilibrium constant for this reaction? Well, in order to do that, we first have to write the expression for the equilibrium constant. So if I look at the equation, N2 plus O2 yields 2NO. And you will notice that I am using a double-headed arrow here. And I want to make a comment on that. When you see it on anything that I've sent to you as far as a test or like on this kind of document here, the double-headed arrow looks like this, and that's another way to represent what I'm actually doing here. So don't let the appearance of that arrow throw you at all. It does look a little different than the one in your textbook. Okay, so when I write the equilibrium constant, just like we did for the rate constant, the products are going to go on the top. So I'm going to take the concentration of nitrogen monoxide, and this time the stoichiometric coefficient is what I'm going to use as the exponent up here like this. So this concentration will be squared, and then on the bottom I will have the concentration of nitrogen and the concentration of oxygen. And just like we did before, those are all in molarity. We also talked the last time about how the units of the rate constant change. The units of the equilibrium constant are going to change also, so you'll have to pay attention to that as you go through this. So if we use the concentrations present at equilibrium that they give us, they tell us that nitrogen is 0.354 molar, so that will go down here. They tell us that oxygen is 0.124 molar. And they tell us that the nitrogen monoxide is 4.51 molar. Whoops, forgot the M. And then that number will need to be squared. So when you type that into your calculator, 4.51 squared divided by 0.354 divided by 0.124, the equilibrium constant turns out to be 463. Now what will the units on that be? Well, on the top I've got molarity squared. On the bottom I have molarity times molarity, which is molarity squared. So in this particular case, there are no units for this particular equilibrium constant for this particular reaction. So the equilibrium constant is 463. Okay? We'll do one more example. Second example on there is giving us 4NH3 plus 7O2 yields 4NO2 plus 6H2O. Here it says the chemist starts with 1.2 molar ammonia, 3.4 molar oxygen, and no nitrogen dioxide or water. He finds the reaction reaches equilibrium when the concentrations of NH3 reach 0.8 molar, the concentration of O2 reaches 2.7 molar, the concentration of NO2 is 0.4 molar, and the concentration of water is 0.6 molar. What is the equilibrium constant for this reaction? Well, once again, I've got to write the overall formula using the balanced equation. So the equilibrium constant, products are going to go on the top. So I'm going to have NO2, and you see a stoichiometric coefficient of 4, so this is going to be raised to the 4th power. Then I have water, H2O. It will be raised to the 6th power. The reactants go on the bottom. You're going to have NH3. and that number will have to be raised to the fourth power. And then you'll have O2, which will have to be raised to the seventh power. Now, if you have not already figured out how to use the power button on your calculator, now would be an excellent time to do that, especially when we have powers that look like this. Most often on the calculator that I have, the button looks like it's a Y to the X button, which it looks like this. And so what happens is if you put in the bottom number and then you hit the Y to the X button and then you hit the power button, enter what the power would be, then that will enable you to calculate what the power is without having to type it in 4 times or 7 times or whatever it is. So for example, if you're trying to figure out what 3 to the 4th is, what you would do is you type in 3, you hit the Y to the X button, and then you hit the 4, and then you can either hit equals or you can hit the times button or you can hit the divide button or whatever your next function is in order to get that number located in there. So I would highly recommend that if you've not already figured out how to use that button, that you work with that and practice with that, because it will make your calculations much easier. Okay, so in this particular problem, you'll notice that they told us what concentrations they started out with, but for an equilibrium concentration or for an equilibrium constant, the initial values are not important. It only matters what the concentrations are at equilibrium, and so that first information that they give us really is completely useless to us. So instead, we're going to use the concentrations that they gave us at equilibrium. So at equilibrium, it says that the ammonia is 1.2, so it's 1.2 to the 4th power, and I forgot the M. I did that last time too, didn't I? I kept forgetting to put that molarity on there. So 1.2 molar to the 4th, and then it says that the yeah, that's right, 0.8. It's not the 1.2. I just told you that was the initial concentration, and we weren't using that. Sorry, I read the wrong place in the problem. We'll read a little bit further in the problem. It says at equilibrium, the concentration is 0.8. So I've got 0.80 molar for the ammonia. Then the concentration of the oxygen is 2.7 molar, and that has to be raised to the 7th power. Then the NO2 is 0.40 molar, and that has to be raised to the 4th power. And then the concentration of water is 0.6 molar, and that will have to be raised to the 6th power. Okay? So, again, as you're typing this in, what you're going to hit is this. You're going to type in 0.4, then the Y to the X button, then the 4, times 0.6, then the Y to the X button, then the 6, divided by 0.8 to the Y to the X button, and then the 4, and then divide it again because it's still on the bottom, 2.7 times Y to the X, and then you're going to hit the 7. And so if you do that correctly, what you should come up with is 2.8 times 10 to the minus 6th. And what are my units here as far as molarity? Well, I'm going to have molarity to the 4th times molarity to the 6th, which is molarity to the 10th on the top. I'm going to have molarity to the 11th on the bottom, so that means I'm going to have 1 molarity in the bottom as my unit. So I've got 2.8 times 10 to the minus 6th over m. So you want to be, what I want you to do is to make sure you pull your calculator out, make sure you can do this and actually get that answer so that you know how to use your calculator properly. Okay? In the next several lessons, we're going to be talking about exactly what these equilibrium constants mean, what they tell us about the reaction, and if there's ever anything that we can ignore in a reaction.